Okay, here we are. This is lesson 4 in our unit on energy and momentum. And we're starting to go from momentum into energy, and we're going to talk about energy considerations. And for many of you, this lesson will be a review of grade 11 work. Okay. And so the concept that we're, of course, discussing is usually where we start when we talk about energy, and that's work. And work is defined as the transfer of energy. Okay. So when work is done, what this means is that a force basically acts on an object and makes it move in the direction of the force. So think about any time that you've gone to push something, you've applied the force to that object and you've displaced it a certain amount. Work is a scalar quantity, okay, so it doesn't have a direction, same as energy. Energy doesn't have a direction. This is different from momentum. And work is represented by the dot product of two vectors. Okay, so it's force dot displacement. And the dot product is one way of kind of multiplying vectors, if you will. Okay. Of course, the units of work are Newton meters, and we call a Newton meter a joule. All right. This dot product we'll talk about in a couple minutes. So here's an example. Let's calculate the work done in these two situations. First, we're going to apply a force of 20 newtons right to a 0.5 kilogram puck as it slides across a frictionless surface. And it's going to go basically from rest to 10 meters per second in 0.2 seconds. So we've got the force. One thing that we need then in this case is the displacement. Here's what we know. And so we can use V1, V2 in time to find the displacement of the object. We find that it's 1 meter once we make our substitutions. And in turn now, we can say that work is equal to force dot displacement. Okay? And what we'll see is that in this case, because the displacement and the force are in the exact same direction, we just multiply these two and we get 20 joules. So that's how much work was done. Here's example B. Here we're going to lift a 57 kilogram motor a distance of 1.4 meters from the ground up to the box of a pickup truck. Okay. So here's what we have. 57 kilograms is the mass that we're dealing with. And we've got a displacement of 1.4 meters. And the question becomes, okay, well, if we're going to calculate the work, we need some force. And of course, what force do we need to lift with if we're going to get this motor up from the ground to a certain distance? Well, in this case, we have to fight the force of gravity. And so that's what we're going to lift with. So what force do we use? Well, we're of course using gravity. And here, force of gravity, of course, we know is equal to mg. And so we can substitute this into our equation for work and make our appropriate substitutions, and we find that this is 782.04 joules, which will of course round off to the correct number of sig figs. Okay, and we continue. Example 2. A horse is pulling a sleigh, okay, and it exerts a force of 100 newtons, but of course that's at an angle of 30 degrees to the ground. Okay, so the horse is pulling up a little bit on this cable as well. Okay, the sleigh moves 30 meters across a horizontal ice surface. Find the work done by the horse. So basically the work that's done on the sleigh by the horse, we're going to calculate that. Now this is a little hiccup here because we got this 30-degree angle and we have to figure out what to do with that. So we're going to say, okay, well, here's 100 newtons and here's the 30 degrees. And of course, if I resolve this force into its x component and into its y component, right? And if I look at the displacement, the sleigh is not displacing in the y direction or in the j hat direction. There is no displacement in the j hat direction. So then one way that I can think about this is I can say, okay, well, my force if I resolve it, is 100 times the cosine of 30 in the I hat direction, plus 100 times the sine of 30 in the j hat direction. And so this is what I get, 86.6 I hat plus 50 j hat. So really, this really points out that, yes, okay, when we're working at an angle, yes, the horse is pulling in the x direction, but because he's kind of pulling up on the cable that attaches himself to the sleigh, he's also pulling up in the y direction as well. And so when we take the dot product of these two vectors, right, basically we're going to multiply the I hats together because they're a unit, and we'll multiply the j hats together. And that's the way that we do this. We take the x component terms and we multiply them. We take the y component terms and we multiply them. And so that's why, that's basically, this is how you do the dot product. So here, 86.6 times 30 is 2598. 50 times 0 is, of course, 0. So if this had a component here, then we would just add these two together, multiply these two together and add them to our result. But of course, that's not the case, because you'll notice that because it doesn't displace in this direction, no work is done in this direction, which makes sense. So here it is. This is the work that's done by the horse on the sleigh. It's 2.6 times 10 to the 3 joules. All right, so moving on, let's talk about this a little bit more, because this whole idea of the dot product is important. So we used algebraic vectors in that question, right? And so we saw that, oh, the dot product kind of takes care of resolving force and displacement into its proper components. This is an alternate method. So here's the definition of the dot product. Any two vectors, when you take the dot product of them, if you take the magnitude of the first and multiply it by the magnitude of the second, so who cares about the direction, just the size of those two vectors, and then you multiply them by the cosine of the angle in between them, basically you get the answer. So you get the exact same thing as what we did before, and we're going to do another example of that. So here it is applied to work. So whenever any two vectors or a force and a displacement are at an angle to each other, the work that's done is basically just the size of the force times the distance times cosine of the angle in between them. Okay, and so basically that's it. That's all we have to do. So this is an alternate method that might be a little bit easier than doing the dot product, and is totally acceptable. So here is another very similar example, and you'll see that it's very similar. So a newspaper carrier pulls a wagon with a force of 275 newtons, but at an angle of 45 degrees to the horizontal. How much work is required to move the wagon 8 meters? So I think you can see this is almost exactly the same type of question. So here it is, 275 newtons, acting at an angle of 45 degrees, right? Here's the displacement, 8 meters. And so what we want to do, we got 275 newtons at 45, displacement is 8. So work is equal to FD cos theta. And we substitute our magnitudes. Now, yes, of course, this 275 is acting at an angle, but when I use this equation, I don't care that it's acting at an angle. All I care about is how big it is, because this little cos theta is going to take care of all that. So you get 1,555.6 joules. So this, you might say, yeah, this is a much easier method, okay? And indeed, if it is, and you're comfortable doing this, then you should use this. All right, so convince yourself. Do the exact same thing right now, but try it using basically the algebraic method that we looked at in example 2, right? Convince yourself it's the same thing. All right, so friction. Friction also does work. And friction is something, this is new for grade 12, because this is something that we did not talk about in grade 11. We always said that everything was frictionless when we talked about energy and work. The force of friction does work as well. However, its action is to remove energy from a system, right? So, and that's why we never considered it in introductory physics, is because it might get a little bit tricky. For our purposes, it's an easy extension, right? So we call friction a non-conservative force because it basically doesn't adhere to the conservation of energy. It takes energy out of a system, okay? And so, but if it's not considered, if we keep on doing the conservation of energy and we don't consider friction, then really this whole thing about the conservation of energy, it's really kind of incomplete. And it's incorrect, and it doesn't match what we observe in the real world. So we need to include it, and in grade 12 this is where we're going to include it. And so let's start practicing how I include energy, the energy loss due to friction. Okay, so here's the last example, or actually second to last example. A 6 kilogram block is pulled to the right along a horizontal surface with a coefficient of friction of 0.15 by a force of 12 newtons for a total distance of 3 meters. How much energy has been transferred to the block? Here's what I know. I know the mass, I know the coefficient of friction, I know the applied force, and I know the displacement. And here's a free body diagram because this is going to be useful. Of course, any force of friction is going to combat the applied force. It's along a horizontal surface. So any work that's done is going to be the difference between the work that the applied force does and the work that friction does. Because friction is going to remove energy, and so we give it a negative sign, it's going to remove energy from the system. And so here we go. Okay, well, we know that the applied force is just, the work done by the applied force is just Fa dot d, and the work done by friction then simply is just the force of friction dot d. And so, okay, let's go and find out what the force of friction is. We know it's mu k times the normal. And of course, the normal in this case is just mg. And it's because in these two directions, there's nothing else acting in the y direction. So these two forces have to balance, especially because the object is only being displaced horizontally. So here it is. We know simply that the cosine, basically the cosine of the angle in between the displacement and Fa is 0, so the cosine of that is just 1. So we get 12 times 3 minus coefficient of friction times the mass times g times the displacement. And we can put all this together and we get 9.5 joules. And so that's how much energy has been done. Now, of course, 36 joules would have been done by the applied force alone if this was a frictionless surface, but that hasn't happened. Friction has removed some of the energy, and so there's not as much in the system. All right, last little topic is power, and this is very much a review. Power is, of course, work over time. Okay, so it's the rate that energy is transferred. So however quickly energy is being transferred to a system, that's known as power. All right, so what power is required for a ski hill chairlift that transports 500 people per hour to an increased elevation of 1,200 meters? All right. Well, here's what we know. The total mass that this thing's going to transport is 500 people times an average of 65 kilograms each. So you get 32,500 kilograms. That's how much mass this thing is moving. The change in height is 1,200 meters. Okay. And the time that it does this in is 1 hour. So 3,600 seconds. So I've converted the 1 hour into seconds because I need to be working in meters, kilograms, seconds. Okay. Here it is. Power is equal to work over time. Well, again, if we're talking about a ski hill and we're talking about a chair lift, we're working against the force of gravity. So here's our force, mg. Here's our displacement, delta h. So this is work right here, and I'm going to divide by time. So I can put this all together. Here's mass, here's g, here's h, here's time. And so what I get is 1.0616 times 10 to the 5th watts. So that's a lot of power, right? Think about a 100-watt light bulb. And of course, this is the reason, this little unit right here, watts is the energy of power, is the unit of power. But if I hadn't have used kilograms, meters, and seconds, then of course this wouldn't have fallen out. And I couldn't have used watts. And we want to be able to use these SI units. So kilograms, meters, seconds, always very important. And that is work and power.